In this example, we're looking at a mechanism which is made up of links OA and AB. OA is pinned to ground at O. NB of AB is constrained to be moving along this vertical guide, straight guide. We have a force F which is applied horizontally to pin A. And what we know is that the system is released from rest when theta is a 0. And the force is a constant, and what we want to find is the speed of the slider there at B when theta's reached this angle of 53.13 degrees. We're looking for change in position, change in speed, so the work energy equation would be a logical choice for an approach to take. With the work energy approach, we're going to be drawing a free body diagram of the entire system. So what I will do is draw the two links and the slider all together. So here's the line of action there for B. We have A along there. We have AB along like this. Let me draw a straighter line here. So the forces that we have acting on this system as a whole are going to be the reactions there at O, OX and OY. We have weight forces like this. We got MG, like this. We have a normal force at the slider B, and of course then our applied force there of F. Our task here is to figure out which forces, if any, do non-conservative work. Well, we know OX and OY, we can take those off of our list because they act at a fixed point. We know here that NB is perpendicular to the path of B, so we can take off that. Our three weight forces, they do work, but we're going to include those calculations, bring in that through the potential. So the only force that does work is the applied force F. So we'll have to do that when we get to that point. So for our work energy equation, we note that the kinetic energy at the beginning is a 0. Because the system is initially at rest, IAR. I'm going to define my datum line for everything. Let's just do everything right through O. So our datum line through O says that the potential for link OA is going to be a minus MGL over 2, the minus sign because it's below the datum line. For AB, it's going to be a minus MG3L over 2. Again, the minus sign is because it's below. And then for B, it's going to be MG times 2L. Again, this is the initial state. Kinetic energy, T2. For link OA, we have a fixed point, so I'm going to choose that, take advantage of that, and say 1/2 IO omega OA squared. So this is for link OA. And then for link AB, we don't really have a fixed point, so what I'm going to do is reference it back to the center of mass G. So this will be 1/2 mvg squared plus 1/2 mass moment of inertia about G times omega AB squared. So this is for our link AB. And G is the midpoint of link AB. And finally, for our block B, it's going to be 1/2 mvb squared like this. There's a lot of kinematics that are going to be needed to be performed in order to relate all the kinematic variables that are appearing there in T2. V2. In V2, we're going to have It's going to be a minus mg L over 2 times cosine of theta. And then for link AB, it's going to be minus mg L cosine of theta plus L over 2 cosine of theta. And then for B, it's going to be minus mg 2 L cosine of theta. For the work that's done by the only force that does work, non-conservative work, is F. So the integration, in theory, that we would do is take F, we project it over the path, on the tangent of the path, and integrate it over the path. Or an alternate form, one in the same, is to take the x component of the force and integrate that over x, and add to it the integral of the y component integrated over the y direction. Well, there is no y component. Maybe I should define what I mean by x and y. I'm going to put x to the right and y up. So there's no y component to that force, so I strike out this. The x component is just that constant magnitude force of F. And so we just need delta XA, where delta XA is just the distance that A has traveled to the right. Well, that's equal to L times sine of theta. So these are the 5 parts that go into our work energy equation. We have a lot of kinematics here, as I mentioned before. We have omega OA, we have VG, we have omega AB, and we have VB. We need to eventually get that work energy equation down to a single unknown, and that's going to be VB. That's what we're trying to find. So we need to come up with a lot of kinematics. Kinematics, though, that we're going to do is very standard stuff for mechanisms. If we would take the vector approach, we're going to talk about 2 different ways of doing the same thing. The vector approach, we'll just do a sketch of that. And that would be to say that the velocity of A can be referenced back to the velocity of O, which is a pin joint, plus omega OA crossed with a vector which goes from O to A. We would write down velocity of B then as being velocity of A plus omega AB crossed with a vector which goes from A to B. And of course, this expression for VA would go into there. And so together we will be able to write down 2 equations, one for I and one for J. And from these we'll solve for 2 variables in terms of the third. So let's say we solve for omega OA and VB in terms of omega AB. That's just a choice. Write 2 in terms of the other one. So we don't get numbers for them at this point, but we get the relationships. In addition, then, we'll say that VG, we can reference that back to point B on link AB. So the velocity of G is equal to velocity of B plus omega AB. We've already got an expression for that from above, crossed with the vector which goes from B to G. And then from that, we will write out VG squared. So that's quite a bit of work. We write down 3 vector equations, do some algebra, and in the end, we get the relationships that we need. An alternate approach, the instant center approach, might be a little bit easier here. So let's see what that would involve. Let me redraw my mechanism. Let me see if I can do a good job here on drawing in lines. Again, this is going to be the path of B. And what I'm going to do then is sketch in OA. And AB. One thing to observe about this is that this angle and this angle are the same. The reason for this is that these two links are the same. So what we know is that the velocity of A is going to end up being perpendicular to line OA. So VA we know is along this line because it's perpendicular to there. We know that the velocity of B is along this guide that we have. So if I construct the perpendiculars to line VA, and construct a perpendicular to line VB, well, where they cross is going to be, that doesn't look very good, so let me try that one again. Where they cross is going to be the instant center for bar AB, which I will call C. So this angle is theta, so is this one, if this helps us out. I can say then that this distance here is 2L sine theta. This distance is L. This is from A to C. So if I write, I'll define an additional angle here, a beta. If I say, I recognize here that beta is going to be the complement of theta. So that's an angle that we know. What I can do is I can use the right relationships here to find out what omega, AB, and OA and those things are, what their relationship are. So what I will say here is that VA is equal to L omega OA, and that's equal to the distance from A to C times omega AB. So this is what this is going to be is the distance of L. So right away we know that omega OA and omega AB are the same. I can therefore say that the speed of B is going to be the distance from B to C times omega AB. So this is going to be the distance of 2L sine theta times omega AB. So that gives me VB. I have the important relationship between omega OA and omega AB. Now all I need to do is be able to write an expression here for the velocity of the midpoint there of G. So I'm going to draw another construction line. I'm going to draw that from the instant center up to this point G. Because the reason I do this is that I know that the velocity of G is perpendicular to this line. So this is VG. So I call this distance D. From the law of cosines, I can say that D squared is equal to L over 2 squared, that's one side of that angle, plus 2L sine theta, the other side adjacent to that angle, minus 2L over 2 2L sine theta times the cosine of the angle between those two sides. So there's that. So from this, I have the numbers it takes to find D, and therefore from here, I say that the speed of E, which is I need in my kinetic energy expression, is going to be equal to D times omega AB. So whenever I write down, let me repeat my kinetic energy expression there at 2. That was going to be equal to 1/2 I-O omega OA squared. That was for OA. For the link AB, it's 1/2 mvg squared plus 1/2 mass moment inertia about g omega AB squared plus 1/2 mvb squared. So I think you can see from here that I have this written in terms of omega AB. This is written in terms of omega B right away. VG, this is written in terms of omega AB, and this we know is exactly equal to omega AB. So this is an expression that's totally in terms of omega AB. So the solve part of this is to take our work energy equation, which is given by T1 plus V1 plus the work going from 1 to 2, non-conservative, is equal to T2 plus V2. We have expressions for V1 and V2. T1 was a 0. And keep in mind that this involves only the unknown of omega AB. So we solve the above for omega AB, and since what we're asked to find in this problem is the speed of B, therefore we can say that VB through the instant center approach is equal to the 2L cosine theta times omega AB, and we've got the answer. The problem is long. The thing that makes the problem long is the kinematics we need to go through. I worked it through 2 different ways, or at least I sketched out it 2 ways. But again, that's going to be the thing that drives the workload of the problem. You could do the vector approach, talked about here. That's one safe and sure way. You may be saving a little bit of effort by finding the instant centers, but that did require us to do a little bit of trig using the law of cosines. In any case, we got a work energy expression all reduced down to a single unknown through the kinematics. We solve that, and we get the answer.